Hello friends, in this video we are going to discuss about the concentration of holes inside the valence band of an intrinsic semiconductor. So, the concentration of holes inside the valence band of an intrinsic semiconductor. As we have discussed earlier, the two factors are there which will determine the concentration of carriers. So, the first factor is the distribution of energy states inside the conduction band or in the valence band. In this case, we will take the valence band because it is the concentration of holes and holes will reside inside the valence band. So, factor 1 is the distribution of energy states inside the valence band. And the factor 2 is what is the probability that these energy states will be occupied by an electron. That is, probability of occupancy of the energy states by the electrons, and this factor 1 is defined by a term that is NV, which is a function of energy, and the probability of occupancy of the energy states by the electrons is defined by Fermi-Dirac distribution function, that is F E. This Fe will determine what will be the probability of finding an electron inside an energy state at any temperature T. So, if we draw the band structure of an intrinsic semiconductor, it will look like this. This is the conduction band and this is the EC energy level and this is the plus infinite energy level. Similarly, we can get a valence band and this is the EV energy level and this is the band gap of the semiconductor. Now, if we see the NVE, it is giving the value of the distribution of the energy states inside the valence band, and it is similar as the NCE, that is the energy state density will be very high in the middle of the valence band. And as we move towards the band edge of the valence band, the density will decreases. So, from this diagram we can see that at the middle of the band gap the density of the energy states is very high, and as we are moving towards the band edge the number of energy states is decreasing. So, if we plot the NVE value with respect to energy, it will look like this one, where at the middle of the band gap the NVE value is very high, and as we are moving towards the band edge, we are getting a low value of NVE. Now the concentration of the holes inside the valence band is denoted by P, and this P will be the integration of minus infinite to EV of NVE into the probability of finding an hole inside this energy state, and it will be 1 minus F of E into dE, because Fe is the, what was Fe? Fe was the probability of occupancy of the energy states by an electron, and 1 minus Fe is equals to probability of finding an hole at any energy state E at some given temperature capital T. So in the valence band we know that there will be only holes, that is why we have used 1 minus Fe, which is giving the probability of the hole occupancy in the energy states. And this total equation, that is the integration from minus infinite to EV minus infinite to EV NV of E into 1 minus Fe into dE, will give the concentration of holes inside the valence band. So if I simplify this equation, before that the NVE value is given by 2 into 2 pi k bar T MP divided by h square to the power 3 by 2, where this MP is the effective mass of the holes inside the valence band. And this k bar is equals to k into q, where k is the Boltzmann constant, and the k bar value is given by 1.38 into 10 to the power minus 23 joule per Kelvin. Now if I put this NV value and Fe value, we will discuss Fe in details in later lectures. So if I put the NVE value and Fe value, then we will get the concentration of holes inside the valence band. So after putting all the values, we will get P is equals to NV into exponential minus EF minus EV divided by KT. So this equation will give the whole concentration of the valence band inside the intrinsic semiconductor. Now from the equation of NV, we know that the NV is proportional to the T to the power 3 by 2. So, this 2 equation is very important with respect to the numericals of this topic, and this is all about the hole concentration in the valence band inside the intrinsic semiconductor. Thank you.